Welcome to qnawire.
So let's see here. We now have this crazy setup here that's very interesting. It's illustrated in the book, and I've tried to reproduce it somewhat in my schematic here. So let's see here. We have, let me just kind of talk through it here a little bit. Um, Coming out of the condenser. So we have let's see here. I didn't really draw that, but we have, this is flow in and out. But let's actually draw it as a closed system here. So flow in and out from cooling water. Um, so here's our condenser. It's being, cooled with cooling water here. We have the output from the turbine coming in, and then we also have the output from the steam traps coming into it. Then we have it coming out to the pump, going through two closed feedwater heaters. And so heating it up some, and then heating it up again. And the heat exchange from those closed feedwater heaters comes from two taps in our two pressure bleeds, or two bleeds in our turbine. One at two different points here. One at 1.4 megapascals and one at 245 kilopascals. And then they come into here, and then we have these steam traps where, again, the steam traps help, you know, if there's any steam left, if this hasn't condensed fully or this hasn't condensed fully, then we will get it here. But again, that's usually in this problem, we're not going to really analyze this. We're going to assume that essentially it's condensed and we got we got full heat transfer here. And this was all kind of condensed. This was condensed liquid, and then this winds up being condensed liquid afterwards, as it goes from 6 to 0.9. Yeah, so here to here. So if there was any steam in here, then we'd kind of trap it into here. So we didn't put it back into there, or put it back into the. I'm not sure why you actually even need to do that, but I'm sure there's a good reason. I'm not a power plant engineer, so I'm not exactly sure why these would come into play. So anyway, you can see in the TS diagram we have pretty big mess here. So anyway, we get this coming out, heating up some more, going into the boiler, heating up some more into a saturated vapor turbine, and then some of it bleeds off here, some of it bleeds off here. The rest of it goes back to condenser, and then the bleed stuff comes in. These all wind up 9, 8, 9, and 11 are saturated vapor or saturated liquid. And so then we come back here, and then we mix that back in with this, and then we go. Right. So how does this look on here? So we go from 1 to 2 to 3, heating up some more, to 4, heating up some more, and then we boil it, or then we keep heating it into the boiler, and then we boil it, and then we superheat it. Come into the turbine. Some comes off here, so the fraction y comes off here, and we have 1 minus y continuing through the turbine. Then we have another fraction z coming off at 7, and we have 1 minus y minus z continuing through the turbine. Then we have 1 minus y minus z going into the condenser. So then at the 6th point, we have 6 going to 9, so it gets basically it cools down, and then it condenses while it's giving up heat. And you can see that we have these temperatures here are the same, which is where kind of inefficiencies would happen, because you wouldn't really have the same temperature coming out here, because you wouldn't get a perfect transfer of energy here, thermal energy. Now, so then from 9, we go to 10, which is basically just is cooling things down a bit. So the steam trap, we cool things down a little bit in there, and we increase some entropy. Now it's odd. I Yeah, I mean, is there? I think. Let's see here. Did I try to remember the whole analysis here? Uh, oh, we never had to calculate the heat transfer out. That is why I didn't do that. Because the heat transfer out, you probably have some you have some heat transfer out here and here too. So you're dumping heat here and here and here. Um, because again, as we go from here to here. So then it comes down to 10, and then it comes to 11, or it mixes in here with stuff coming off from 7. So 7 and 10 is coming here and here mixed, and then we go to 11, and then we come down here to 12 through this steam trap, and then this mixes with this in the condenser, so we have the so then we have everything we need, I think. So hopefully I've described this system in enough detail that you can follow what is going on here. We're also told what Y is. So whatever, it's 14.5% basically. So about 14.5% is coming out of here. We don't know what Z is yet, but we'll figure that out. Okay, so let's start with the pump. So we can get the power into the pump as usual. Then we can get the enthalpy at 2 as usual. The enthalpy at 3 and at 11 are the same, again, because we're assuming perfect heat, transfer energy here. And it's also the same as the enthalpy at 12, we're going to assume. Let's see here. And that all winds up being this plus this. No. Enthalpy at 3 we can get because what are we using at 3 here? I didn't write a lot of this. Probably I should have written more of this stuff down. Oh yeah, because it's basically at 11 it is a condensed. It's a saturated fluid at 11, and we know the enthalpy at 11 and 3 and 12 are going to be the same. We're going to assume that they're the same. So let's see here. Then we get the enthalpy at 4, 8, 4, 9, and 10. Okay, so then 4, 9, and 10. Because we know, let's see, 4 again, it's now again at 4, not 9, we have a saturated liquid. So and then at 10, again, we're assuming that we're not having any changes there. This is kind of a enthalpy, line of constant enthalpy. And then at 4, it's also the same. Okay, so again, these are a lot of assumptions that were not necessarily told to us, but we're kind of, making them anyway because again, there's you can we're assuming that there's no heat transfer here, which is kind of weird by assuming that these are the same because there's a drop in temperature, of course. But if you did an energy balance on this and there's no work, no external work and no heat transfer, then these enthalpies would be the same. So it's kind of, I'm not exactly sure how our steam trap works, but anyway, enthalpy, we're basically assuming there's no heat energy flowing, no heat flowing in or out here or here. Okay, and then we have perfect heat transfer through there. Okay, so if we do conservation of energy on the closed feed water heaters, so let's see here. I should put in, there's Y, so this is Y and this is Z, and this is 1 minus Y minus Z. So we have into this one, you can see we have H2. Okay, so that's that winds up being the full flow, right, going into the turbine. So that the coefficient of 1 here. Then we have Z fraction of it coming off here. So that's in H7. So that's the enthalpy coming in from here. Enthalpy coming in from 10. This has a flow fraction of Y. All right. And then the enthalpy going out, we have again a flow fraction of 1 here, because everything's going out. And then everything gets recombined back in, essentially back in here. These combine here, so we have y plus z going in here, and 1 minus y plus 1 minus y minus z coming here, so we have 1 coming out here. So we have, so then we have, so that going in to this guy. Let's see here. I think we're basically yeah. So we have let's see here. 3. Oh yeah, no, this is coming out. This is what we're coming out. And then coming out is also 11, and that's y plus z, the fraction of the flow. Okay, so we're looking here. So we have this energy balance. And again, using a lot of conservation of masses. We know everything in here now except for z. Now, where did we get H7? H7 is Y, I think, did I actually get H7 from somewhere? I obviously did, but I didn't write it down here. H7 we know because, oh, yeah, there's a whole lot of stuff in this problem that I didn't really go through because it's the same as in all the previous problem. If we know the enthalpy at 5, and we know this is 100% efficient, so we can then get the everything we need to know at 6, 7, and 8, because we know the pressures, and we know now we know the temperature here, I believe. The temperature at, and there's the boiler at, let's see here. No, did they tell us that? No. How did we get that? So we know the pressure. What is it that we know to get that? How did I how did I find that? Let's see here. 7. How did I find the enthalpy at 5? So the enthalpy at 7 is going to be, let's see here. We know the pressure there, and we know, let's see here. It's close. Power cycles. Okay, we got mass flow rate. Yeah, that's and the fraction is extracted at 1400. Yeah, and let's see here. Use the data provided in the tables. Oh. Yeah, that's right. I forgot that they gave us a whole table of stuff in the book. That makes a lot of sense. That's where I got all this stuff. Oh, I didn't read it. I wasn't paying attention to the book. There's a whole bunch of stuff in the book in the table. that gives us this information to help us out. That's why I got where I didn't copy all that information into this problem. That is why. Okay, got that. So we have H7. They gave us H7. What do you know? Anyway, we can get everything we have here. We know everything but Z, so we can find Z, and that winds up being about 9.8%. Okay, so then we can do an energy balance on, let's see, this is the condenser. And so then this is the cooling water flow rate here. And so we have stuff, enthalpy coming in here and here and here. Right? Has to be equal to the enthalpy going out here and here. So we are told what m dot, we know m dot 5. And so we can get all of these other flow rates except for m dot w in terms of m dot 5 and y and z, right? Because of just conservation of mass at various points. So, you know, m dot 8 is, where is 8 here? So it's m dot 5 times 1 minus y minus z. Okay. M dot 12 is, this winds up being y plus z times m dot 5. And then MH1 is just m dot 5 in the end. This combined to give. So again, we get all of these mass flows too. And in the end, we know everything in here except the mass flow rate of the cooling water. And again, we can figure out that the cooling water, the change in temperature of the cooling water was given to us as 10 degrees C. And yeah, that was given in the problem. So cooling water temperature rises 10 degrees C. So we know what this is, and we can just assume a heat capacity of water. Anyway, we can plug all this in. And so basically this here is HW1 minus, well, HW2 minus HW1. Right? So the difference in the enthalpy of the cooling water in and out. Anyway, we get a flow rate of 3,147 kilograms per second. So we have a whole lot of cooling water flowing through here. Much more than we actually have working fluid flowing in here. Now, net power out of the turbine. Again, energy balance on the turbine. So here's the specific work out of the turbine. And so we wind up with, again, basically an energy balance on the turbine. And we wind up with this value, 1,245.5 kilojoules per kilogram. We know the net because we know the work into the pump right here. So we can subtract that out. We get this. And then we know the mass flow rate, so we can get the power out. So we get about 93 megawatts of power out of this. The heat transfer into the boiler. Into the boiler, we know we're just going from 4 to 5. So we know the H is at these. We know the enthalpy at each state. And so that's just the mass flow rate through the boiler times the enthalpy change in the boiler. And that we get 230 megawatts. And so this divided by this gives us our efficiency, and that is 40.4%.